Okay, in this lecture and the lecture to follow, we are going to be doing Laplace transforms and then solving our partial differential equations by Laplace transforms. So we have the same setup. That is, right now we are trying to solve a PDE. And the solution to the PDE is over here. But there's an obstacle. In other words, it's just plain hard. So we do a Laplace transform. And then this changes our problem into an ODE. And then we solve it using any method of ODEs that we know to get the solution to the ODE. And then we take the Laplace inverse transform. To go back. Now the problem is it's so much easier to take Fourier inverse transforms than it is a Laplace inverse transform, because a Laplace inverse transform is called the Mellon transform. I think that's the way you spell it. I don't remember. I don't use it much. And these are done in complex space. So these are hard. So we are sure to use tables for this. Okay, that's the only way you want to do it. Okay, so if you remember, the requirements for a Fourier transform was that basically after some point, the Fourier transform, after some point, the function had to be zero or going to zero in order to be able to take the Fourier transform. So we have something similar for the Laplace transform. So given f of t such that we can say the absolute value of f of t is less than m times e to the L for some fixed m and L. Okay, then we can take the Laplace transform. So in other words, our function that we're taking the Laplace transform cannot grow any faster than exponentially. Okay, so we compute the Laplace transform. This is the integral from 0 to infinity of f of t e to the minus st dt. And we're going to call this capital F of s. So our variable for the Laplace transform is s. And if you remember, our variable for the Fourier transform was omega. Okay. So the Laplace inverse transform of capital F of s is just equal to little f of t. Okay, and again, we gotta use tables because that can be very difficult. Okay, so some very common ones. I'm gonna do a couple. I'll do this first one. Here's an example. So f of t is equal to 1. So therefore, the Laplace transform of f of t is the integral from 0 to infinity of e to the minus st dt. But that's just the limit as b approaches infinity of the integral from 0 to infinity of e to the minus st, integral from 0 to b dt. So that is the limit as b approaches infinity. I'm going to get minus 1 over s e to the minus st evaluated between 0 and b. So that's the limit as b approaches infinity of minus 1 over s. Then I'm going to get 1 over e to the s times b minus 1. And the assumption here is s, what's the assumption? S is always bigger than, no, the assumption S is positive. So therefore, this term goes to 0 as b goes to infinity. So I just get 1 over s. Another example, I'm going to let f of t equal to e to the at. Okay. So therefore, the Laplace transform of f of t is the integral between 0 to infinity of e to the at times e to the minus st dt. And here the assumption is s is bigger than whatever a you're looking at. So this becomes the limit as b approaches infinity of the integral from 0 to b of e to the minus s minus a t dt. That's the limit as b approaches infinity of minus 1 over s minus a e to the minus s minus a t evaluate between 0 and b. So that's the limit as b approaches infinity of minus 1 over s minus a. I'm going to get 1 over e to the s minus a times b minus 1. And again, since s is bigger than a, that thing goes to 0. So I just get 1 over s minus a. All right, so there are many tables of Laplace transforms. Okay, many tables of Laplace transforms. I believe there's several of them that we will use. Okay. Now let's look at Laplace transforms of derivatives. Okay, so let's take the Laplace transform of f prime of t. Well, that is the integral from 0 to infinity of f prime of t e to the minus st dt. So I'm going to let u equal e to the minus st dt. And I'm going to let dv equal to f prime. That's wrong. I'm going to let this be f prime of t dt. Then du going to be minus s e to the minus st dt. And v is just going to be f of t. So we're doing integration by parts. So therefore, this is going to be the limit as b approaches infinity, the integral from 0 to b of f prime of t e to the minus st dt. But that is the limit as b approaches infinity. So we're going to get uv. So uv is going to be f of t e to the minus st evaluated between 0 and b minus the integral to 0 to b of v, which is f of t, du. And du is minus s e to the minus st dt. So this now is going to equal the limit as b approaches infinity. I'm going to get f of t, f of b, and then it's going to be over e to the s times b minus f of 0 times e to the 0. Then I'm going to get plus the integral from 0 to b of s e f of t e to the minus st dt. Okay, so now I'm going to get, well, this term is going to go to 0. So I'm going to get 0. Then I'm going to get minus f of 0. And then I'm going to get plus the limit as b plus s times the limit. As b approaches infinity, the integral from 0 to b of f of t e to the minus st dt. Well, we just did this. That's just big F of s. So the Laplace transform of f prime of t turns out to be minus f of 0 plus s times f of s. And we normally write it as s f of s minus f of 0. Okay. All right. So now we can take the Laplace transform of f double prime of s. That's the integral from 0 to infinity of f double prime of, this is a t. E to the minus st dt. So that's the limit. B approaches infinity. The integral from 0 to b of f double prime at t e to the minus st dt. Okay, so we're going to let u equal e to the minus st, and then dv is going to be f double prime at t dt. Du is the same, minus s e to the minus st dt. But v, how does it do that? I think there we go. So the Laplace transform of f double prime of t turns out to be the limit as t approaches infinity. And then I'm going to get u times v. U is e, so that's going to be f double prime. Oh, v is f prime. F prime of t, e to the minus st, evaluate between 0 and b, minus the integral between 0 and b of minus s e to the minus st times f prime of t dt. Now this is going to equal the limit. How did I change the t? This should be a b. I know how because when I'm teaching my Calc 1-2 students, they use t in the book. But I've always used b because I do limits of Laplace transforms, and so I don't want t to go to infinity. So this is b goes to infinity. So the first term is f prime at b over e to the sb minus f prime at 0 times, that's it. Then I'm going to get minus plus s, the integral from 0 to b of f prime of t e to the minus st dt. So this term's going to go to 0. So now I'm going to get minus f prime at 0 plus s, and that thing right there is Laplace transform of f prime at t. So this is going to give me minus f prime at 0 minus s times negative f at 0 this is a plus, okay, plus s times the Laplace transform. So therefore, I get the Laplace transform of f prime double prime of t is equal to minus f prime at 0 minus s times f at 0 plus s squared, the Laplace transform of s. And in fact, we have a recursion formula. If we take the Laplace transform of f triple prime at t, it's going to be minus f double prime at 0 minus s times f prime at 0 minus f at 0 plus s cubed times f of s. Okay. Any questions about that?
No.
Okay. All right. So how do we take the Laplace transform of a function of two variables? Well, the Laplace transform is on t, so we're not going to worry about the x. X goes along for the ride. So the Laplace transform of u and xt is the integral from 0 to infinity of u of xt e to the minus st dt. And we're going to call that capital U of x and s. The Laplace transform of u sub t of x and t is going to be minus u at x and 0 plus s times the Laplace transform of x and s. The Laplace transform of u sub tt of x and t going to be minus u sub t, that's the one derivative of x and 0, minus u, minus s, times u at x and 0, plus x squared, capital U of x and s. The Laplace transform of u sub x of x and t is the integral from 0 to infinity of u sub x of x and t e to the minus st dt. But that's the partial with respect to x of the integral from 0 to infinity of u of x and t e to the minus st dt. And that's going to equal capital U sub x of x and s. So x derivatives just come back out, just like t derivatives did on the Fourier. Laplace transform of u sub xx of x and t is capital U xx of x and s. Now the nice thing about Laplace transforms is that Laplace transforms just throw the initial condition right into the problem. Literally, just snatch it up, okay? Fourier transforms, we don't have to worry about boundary conditions because we assume everything goes to 0. And it's on the interval minus infinity to infinity. But Laplace transforms are on the interval 0 to infinity. Okay, so let's recall this problem. U sub t plus u sub x equals 0. 0 less than x oh, sorry, this is minus infinity. less than positive 3, t is greater than 0, and u of x and 0 is equal to e to the minus x. Wait a minute. Why do I want to do that hideous example? Because that's the hideous example I have. Because I don't have anything nicer right now. Okay. This example does not show you why you would want to use the Laplace transform. Okay, this is the Laplace transform is a very nice way to solve some problems, but this example does not promote the Laplace transform. Okay, let me just tell you that. You're gonna be like, there's no way I would use the Laplace transform ever. But in many problems, it is wonderful. It's not in this one. Let's just say it's not in this one. Okay. All right. So we had the partial of u with respect to t plus the partial of u with respect to x dx dt is equal to 0. So here's the partial of u with respect to t, and here is the partial of u with respect to x. So this equation implies two things. This is du dt. So this implies du dt is equal to 0, and dx dt is equal to 1. And here we're assuming u is a function of x, which is a function, oh, come on, you're kidding me, undo. Okay. So dx dt equal to 1 implies that x is equal to t plus a constant. And x equaling to x naught when t is equal to 0 says that x is equal to t plus x naught. So our characteristics, these are our characteristics. So this takes us way back to method of characteristics. Okay, du dt equaling 0 implies u is just a constant. So now u of x naught 0 is equal to e to the minus x naught. And this is also a constant. But since u is a constant, that implies then that k is e to the minus x naught. So we get u of x and t is e to the minus x naught. But that's e to the minus x minus t. So we have a wave propagating to the right. Okay. All right. So that's all nice and easy. So what I'm getting ready to do, although it's a teachable moment, is not a pleasurable moment. Okay. So let's try Laplace transform. Okay, so we're going to take the Laplace transform of the PDE. So when I do that, I'm going to get S, capital U of X and S, minus little u of X and 0 is going to plus the Laplace transform of U sub X is U sub X of X and S, and that equals 0. Okay. So now U of X and 0 was e to the negative x. So now I'm going to get U sub X at X and S plus S U of X and S is equal to U of X and 0. So that's e to the negative x. I feel like I forgot something. Oh, I did. I forgot an initial. I forgot. Aha. No. You say aha, but I don't have an aha moment. Aha. No, I still don't have an aha moment. Why do I know what U of because this is that's why it looks so bad, because this is a different problem. Okay, now I know why my notes are messed up. Ha ha, life is good. Plus S U of X and S is equal to e to the minus x. Okay, that's a different problem. Now I know why I'm confused, why I was confused in my notes. I got it now. All right, so we need an integration factor. So our integration factor mu is going to be e to the integral of p of x dx. And that's e to the s x. And so so this side becomes the derivative with respect to x of e to the sx times capital U of x and s. And this side becomes e to the sx times e to the minus x, which becomes e to the s minus 1 times x. Okay. So we integrate both sides and we get e to the sx, capital U of x and s becomes 1 over s minus 1 e to the s minus 1 times x plus a constant. So therefore U of x and s becomes 1 over s minus 1 e to the s, when I multiply by minus s, I'm going to get e to the minus x plus a constant e I am deviating from my notes and I am having an issue. So now I know why I'm having an issue. Let me go back and tell you why I'm having an issue. And I see where my mistake is. This problem right here, we had to be on the interval. This problem right here does not make sense if x can be negative. So now I know why. Okay, so remember I told you my notes seem weird. Okay, so this problem cannot be on the interval minus infinity to infinity, because if x is equal to, so the only thing I can do with this problem I could make it e to the minus absolute value of x. Yes, let's do that. Let's see if we can fix it, if we can salvage this. So if we can salvage this, this becomes e to the absolute minus absolute value of x. Trying to salvage this problem. I don't want to throw it all away. Which would make this okay. All right, so we're trying to salvage this problem. Trying to salvage this problem. I don't know if we're going to be able to. I don't know if I'm going to be able to save this. And the reason why I say that is because, well, this would have to be absolute value, which would have to make this, okay, it's salvageable. You're going to have one answer for x is greater than 0 and another answer for x is less than 0. That's the only way to save this. There's no other way to save it. Okay. So we'll solve the problem. This is as x goes to minus infinity. No. Does it matter? I don't think it matters. It doesn't matter. Put absolute value in. Yep, there we go. I've got it. Okay. Okay. Here we go. Now, since e to the minus sx goes to infinity as x goes to infinity, c has to be equal to 0. Otherwise, that term's going to blow up. So now you get u of x and s is equal to 1 over s minus 1 e to the minus absolute value of x. And I still don't think this is going to work. I still think it's got a fudge in it. And I'm going to have to fix it next time. But let me look at this Laplace transform table real quick. A 66, a Laplace transform of 1 over a Laplace inverse transform of 1 over S minus A there is a formula for that. That is e to the AT. So something's not right. I got to figure it out. Inverse transform of this. But that's e to the minus absolute value of x, and this becomes e to the t. So something's screwy. I got to fix this. I got to fix that. This is not the first time I've blubbed, but you know that. We all do it.